All right, today we're going to crack open one of the most important and, yeah, famously tricky algorithms in all of computer science, Paxos. Now, you've probably never heard of it, but trust me, it's the invisible engine that makes sure the services you use every single day, from your bank to your cloud storage, don't just fall apart. So let's pull back the curtain and see how this thing actually works. To really get why we even need something as complex as Paxos, we have to start with a super basic question. I mean, in a world of incredibly powerful computers, why can't we just have one giant, all-powerful machine running a service? Why do we have to make everything so complicated by spreading the work across tons of different computers? And that's exactly where the journey to Paxos begins. It all starts with the fundamental limits of a single machine. It turns out that whole one computer dream, well, it hits a very real, very hard wall. So picture this. You've built this amazing new app. It's a huge success. It's blowing up. People are flocking to it, which is great, but that success comes with a price. Your one lonely server is getting totally overwhelmed. It's running out of memory, the CPU is pegged at 100%, everything is just grinding to a halt. So what do? Well, you can upgrade it, right? You can add more RAM, get a faster processor. That's called vertical scaling. But there's a limit to that. You just can't build an infinitely powerful computer. The only real solution if you want massive scale is to go horizontal, to use many computers all working together. And that, right there, is where a whole new, much harder problem begins. So this leads us right to the core challenge. When you've got a whole fleet of computers, how in the world do you get them all to agree on, well, anything? How do you make sure they all have the exact same correct data? This is the quest for what computer scientists call consensus. And there's a perfect analogy for this. Think about trying to get a group of your friends to decide what to do for the afternoon. The goal isn't for you to get your way. The goal is for the entire group to agree to do one single thing together, even if it wasn't your first choice. That, in a nutshell, is consensus. And you can see how that process breaks down. You start with disagreement. Some friends want to see a movie, others want to grab dinner. Then a little persuasion happens, and people start changing their minds. The second a majority agrees on dinner, that's it. The decision is made. Everyone commits to dinner, and the group can move forward. That is exactly what computers in a distributed system need to be able to do. So how does Paxos actually pull this off? Well, here's our game plan. First, we're going to meet the players involved. Then we'll walk through a successful proposal, see what happens when things get messy and proposals collide, and finally, we'll understand how this all comes together to build an indestructible ledger. All right, let's meet the cast of characters. In any given Paxos run, there are 3 key roles. You can think of them as different jobs that servers can do to help the group come to a decision. First up, you've got proposers. These are the ones suggesting a value, like, hey, let's go to dinner. Then you have the acceptors, who are basically the voters. They're the ones who actually form the consensus. And finally, you have learners, who just need to find out what the final decision was. And here's a crucial point. A single physical server can, and very often does, play all 3 of these roles at the same time. Now, here is the magic rule. This is the simple mathematical trick that makes Paxos work. If you have 5 acceptors, any 2 majorities, so any 2 groups of 3, are guaranteed to overlap by at least 1 member. That little overlap you see right there, that's the secret sauce. That's the guarantee that ensures Paxos can't make a mistake. Keep this in mind, because it's about to become very, very important. Okay, so let's walk through this. We'll start with the happy path. What does Paxos look like when everything goes smoothly, when a single proposal just sails through without any interruptions or conflicts? It all happens in 2 phases. Phase 1 is what we call the promise phase. A proposer wants to suggest a value, so it first sends out a prepare message with a unique ID number. Let's just say the number is 5. The acceptors get this message, and they look at the number. If they haven't seen a higher number yet, they make a promise. They say, okay, I promise I won't listen to any proposal with a number lower than 5. Then they send that promise right back. So, once our proposer gets a majority of those promises, it knows it has the green light. It can now move to phase 2, the acceptance phase. It sends out an acceptor request, but this time it includes the proposal number 5 and the actual value it wants everyone to agree on. Let's say the word cat. The acceptors get this, they see it's for proposal 5, which they promise to listen to, and they formally accept it, replying back with accepted. And that's it. The moment a majority of acceptors send back that accepted message, consensus is reached.
The decided value forever and for all time for this particular run is cat. The deal is done.
But the real world is messy. So what happens when two different proposers try to get a value accepted at the exact same time? This is where the true genius of this algorithm really shines through.
Let's say proposer A sends a prepare with ID 7, while proposer B sends one with ID 6. Well, any acceptor that saw ID 7 has now promised to ignore anything lower. So when that prepare 6 message shows up, they just toss it. Proposer A wins the promise phase, simply because it had a higher number. Proposer B's attempt, for now, is dead in the water.
But what if a value had already been accepted in a previous round? This, right here, is the most important rule in all of Paxos. It's what guarantees safety. When an acceptor makes a new promise to a new proposer, it also tells that proposer about any value it already accepted. It essentially piggybacks that old information onto its new promise. And this is what creates that unbreakable chain. A new proposer might come along and win the promise phase with a higher ID, sure. But if it learns from those promises that the value cat was already chosen, it is now forced to abandon its own value and propose cat instead. This rule makes it physically impossible for the system to ever overwrite a decided value. Once cat is chosen, all future proposals will be forced to converge on cat. Okay, so this seems kind of limited, right? The algorithm only agrees on one single unchanging value. How on earth is that useful for something dynamic, like, say, your bank account balance? This is the final, brilliant piece of the puzzle. We have this incredibly powerful tool for agreeing on one thing forever. But most of the data we care about needs to change all the time. A bank balance goes up, it goes down. So how do we bridge that gap? The solution is so clever. Instead of agreeing on just one value, you agree on a sequence of values. You use Paxos to agree on the contents of a log or a ledger, one entry at a time. So, to set the initial balance, you run Paxos for log position 0. Then, when a deposit comes in, you start a new Paxos run for log position 1. Each transaction becomes its own separate consensus decision. And that's the key takeaway right there. Paxos itself only decides on one value at a time, but by running it over and over and over again for each new line in a ledger, you can build a dynamic, complex, and totally consistent history of events that is shared and agreed upon by an entire fleet of computers. This is the foundation of almost every modern distributed database. And that's Paxos. It's this beautiful solution that guarantees consistency through a clever dance of promises and proposals. And it all hinges on that one simple mathematical fact. Any two majorities will always overlap. Which kind of leaves you wondering, right? If a rule that simple can solve a problem this complex, what other huge challenges in technology and maybe even beyond are just waiting for us to find their own surprisingly simple, elegant solution?